So we can come up with this abstract description of what we have done in both these problems. So here is an abstract description of the greedy method. So we want to identify a subset of a set of objects which we will call A. Okay, so A is the starting, is the universe of all objects. Okay, and there are n of them. Right? So that describes these two parameters A and n. So what we do is we start by initializing the solution to be empty. So we initially have selected nothing. Now all the magic in greedy happens because of this function which chooses the next item to consider. So in the change making problem, we chose the next highest denomination node that we have not seen before, and in the task scheduling problem, we chose the next task in order of starting time. Having chosen this task, we have an existing solution incrementally built up. So what we have to see is whether this solution can be extended to X or not. In the change making problem, this means that we have to check whether the next node is actually less than the current balance. In the task scheduling problem, we have to check whether we can put it into one of the current machines or not. Of course, in the task scheduling problem, it's always feasible. The only question is whether the solution has to be extended by adding one more machine. So once we have checked that it is feasible, then we will extend the solution. So this is abstractly captured by this union operation. So what union encapsulates is that you want to incorporate X into the solution and you want to update the state or the objective function or various things. So in the change making problem, okay, you would update the current balance remaining by reducing the amount by the new denomination that you have chosen to use. In the task allocation problem, the machine that has now been allocated will now have a new ending time when it becomes free. So for each machine, we have to keep track of the ending time, right? And we have to choose that machine which becomes free next. So going back, just to emphasize, so if you look at our change making problem, okay, so in our change making problem, the set A, okay, is actually the set of denominations 500, 100, 50, 20, 10, 5, 2 and 1. Okay, and now this step X equal to select A is to pick the next denomination. And then this test of whether feasible solution of X is true is if the denomination is less than or equal to the current balance. Okay. And finally, the solution is updated. So one is we count the number of multiples of the current denomination that go in, so whether we can use 1 or 2 or how many, okay, and we reduce the balance by this amount. Okay, so this is how the change making problem would fit into the general strategy that we just outlined. What about the task scheduling problem? So here, what is A? Okay, so A, if you think about it, so if I have task I assigned to machine J, right, I can think about it as a pair I comma J. So I comma J means task I is assigned to machine J. So now we know that there are 1 to n tasks, okay, and at most 1 to n machines. Okay? And what we want to do is, of course, process the tasks assuming that they are in starting order. So A would be the set of all possibilities starting with assigning 1 to 1 or 1 to 2 or 1 to n, okay, then assigning 2 to 1 or 2 to n, and so on, and then finally assigning task n to machine 1 or task n to machine n. So we have these n squared possible values of assignment, and here the idea is that the jobs are ordered by starting time. So we already have fixed the order. Okay? So this makes it simpler to think about the next thing that we have to say. So jobs are ordered by starting time. So therefore now the select is easy. You just pick the next pair ij from the list, because we already ensured that the order is good. Okay, and now a pair is feasible, so I can add this pair. One, the task I is not yet scheduled. I mean, there's no point in scheduling the same task twice. So it has not been allocated to a machine. Okay, and machine J is idle. That is, when task I has to start, machine J should be available. If this is true, I can add it to the solution. If this is not true, I have to go to ij plus 1. Okay, and remember that there are n machines, so for some I this will always work. And of course, the union is easy now. So when I do union solution X, this just means add ij to the solution set. And I have to update the next idle time of machine J. Right? So these are the two ways in which we can take the two problems that we looked at and fit them into this general paradigm that we have been talking about. So just to emphasize that greedy on its own is not automatically the most efficient thing. The first greedy solution may not be the most efficient thing. So let's look at the task scheduling problem a little more carefully. Okay, so as stated, the way we described it, A has n squared pairs, right? So we start from 1 1 and we go up to n n. Okay, so this takes therefore time O n squared, because I have to go through in general these n squared pairs. And in particular, the foolish thing is that when I have allocated a task I look at all other machines for task I, even though I know that I don't have to allocate them before I go to task I plus 1. Okay, so we can actually improve this, okay, to improve this to O n log n. Now we can't do better than n log n, at least the way we have done this, because sorting the tasks initially is of course O n log n, right? So we have to initially reorder the tasks in ascending order of starting time before we start operating on them. So that itself takes n log n. Now the question is, can we do the allocation also in n log n? And here what you need to do is to use a heap. Okay, so you keep the next idle time of each machine, what is called a min heap. Okay, so the heap will give you the minimum element in constant in log n time. Okay, so in the next idle time of each machine is kept in a min heap. So what you do is that you extract the minimum and you update the heap with a new value, right? And now this takes time log n for each job. So you multiply it by n jobs, and so you can do the allocation of the n jobs in time n log n. So you can do the initial sorting in n log n, you can also do the allocation n log n. So what this shows is that just because you have a greedy strategy doesn't mean you can stop. You have to look at the greedy strategy and see how to optimally implement the step within the strategy. So here the problem is not so much, there are two things here. The number of things to consider itself is not optimal if you choose all pairs 1 1 to nn, right? So there itself you have n squared pairs, and even if you have chosen optimally, you need a quick way in which to update and find out which machine to use. So here you can actually do it in n log n time. Right? So to summarize, okay, so we have this greedy approach to optimization. So what we do is we choose one element at a time by some local criterion, that we are not looking at the, see, we are looking, trying to globally optimize something. Overall we want to maximize our revenue, or overall we want to put the maximum number of things into a container, or so on. But instead we look at the next thing that we're going to do. Is this the biggest one remaining? Is this the earliest job to be done next, and so on. So we have some local criterion by which we choose the next element. Okay, and now the crucial thing is that if we proceed in this order without backtracking, without going back and changing our choices, we achieve optimality. So we make one pass over our sequence of choices, and in that one pass we either choose to keep or not keep each item that we look at, and without going back we make an optimum set of choices. So what remains, of course, in all these things is to prove the optimality. We haven't proved the optimality for either of the problems we have looked at in this lecture, but we will give proofs for some of the examples we'll see in future lectures.